Hello students, this is Dr. Anita Raj welcoming you for another session in coordination compounds. In the previous video, we saw how VBT explained the geometry and hybridization of square planar complexes, and today we shall see how this same VBT explains the octahedral complexes. Okay, for that I have chosen Hexa Cyanido Ferrate 3 ion as an example. Actually, the theory given by Lewis explained the structure of molecules, however, it failed to explain the chemical bond formation. Similarly, VSEPR theory explained the shape of simple molecules, but it failed to explain the geometry of complex molecules. Hence, the scientists had introduced this VBT, that is valence bond theory, to overcome the limitations, all these limitations. Okay. Shall move on into the topic now. The complex I have chosen today or I have taken today is FeCN6 3-, that is Hexa Cyanido Ferrate 3 ion. Okay, right. What is the central metal atom here? Actually, it's not the atom, actually it is the ion. Okay, so the central metal ion is Fe3+. Okay, it is Fe3+. Since the oxidation state of this Fe, okay, this oxidation state of Fe in the complex, in this complex is plus 3. How it is plus 3? So we shall see FeCN6 3-, is it not? How will you find out the oxidation number for this? Let us we want to know the oxidation number of ion, is it not Fe? So we shall take it as X. Then for cyanide is Cn, the charge is -1. So there are 6 cyanide ions, is it not? So it is -6 is equal to, what is the overall charge here? It is -3. Okay, so now X is equal to -3 plus 6, that's equal to plus 3. So this is how we should find out the oxidation number of the central metal atom or the ion. Okay, so here the oxidation number of this Fe is plus 3, right? That's why we are having this as ion. Central metal ion is Fe3+. Okay, now next is ligand. What is the ligand present here? It is a cyanide ion, Cn. Okay, how many ligands are there? 6 ligands are there. Okay, so Cn, it is the ligand and there are 6 in number. Okay, and this Fe3+ is surrounded by 6 Cn- ions. Understood? So this Fe3+ is surrounded by 6 Cn- ions. Okay, so they are the ligands. Now what's the next one? Outer electronic configuration of Fe3+. We are supposed to write the outer electronic configuration of Fe3+. See here, first of all, the atomic number of Fe. What is the atomic number of Fe? It is 26. Okay, so if you are writing the electronic configuration of this, first you should know the nearest noble gas. Okay, what of iron? Which is the nearest noble gas? It is argon. Okay, so argon, what is the atomic number of argon? It is 18. Okay, so let us write here 18. So what about the rest of the things? We are having already argon 18, so 3d 6 and 4s2, is it not? 4s2. So this is the electronic configuration of iron. Okay, but we want to write the outer electronic configuration of this Fe3+. When you will get Fe3+, when 3 electrons are removed, we will be getting Fe3+, is it not? So after removal of 3 electrons, so 2 electrons from here and 1 electron from d orbital will be removed. So finally we will be getting the outermost electronic configuration as 3d 5 4s 0. Okay, this is the outer electronic configuration of Fe3+. Understood? Right? Okay, next we are going to write the outer orbital of the metal ion. How the electrons are arranged in this outer orbitals. Okay, so we are having 3d5. So based upon Hund's rule of maximum multiplicity, the electrons will be arranged. What is Hund's rule of maximum multiplicity states? So it states that the electrons will be arranged singly first, and after getting accommodated in all the orbitals, and then it starts to pair up. Okay, since here we are having only 5 electrons, the electrons will be singly occupying all the orbitals. Okay, according to Hund's rule of maximum multiplicity. Okay, this is how it will be getting arranged. Understood? Okay, So here in 4s0 we don't have any electron, so it will be empty. Okay. So next comes the nature of the ligand. Since see what is the ligand here, it is a CN. Okay, CN, cyanide ion, it is the ligand, and it is a strong field ligand. CN is a strong field ligand. Okay, so strong field ligand. Okay, since it is a strong field ligand, it passes up the electrons of Fe3+ against Hund's rule of maximum multiplicity. Mean, see this, it will be started, since it is a strong field ligand, this will be having a capacity, or it will force the electrons to get paired up. Understood? Next we are going to write the outer orbitals of Fe3+ ion in the presence of ligand. As I told you earlier, the ligand is a strong field ligand. First what happens, the electrons will be arranged singly, is it not? All 5 electron orbitals will be having single electron, since it is 3d5. But in the presence of strong field ligand, this electrons will start to pair up. Okay, so how the pairing takes place? These two electrons will be getting accommodated in this. Okay, 1 and 2. So here, so according to this VBT or valence band theory, the central metal ion should be ready with 6 vacant orbitals. Since in this complex we are having 6 ligands, okay, CN ligands. How many ligands are there? 6 ligands. See, all these ligands will be contributing one lone pair of electron. Okay, it will be giving a pair of electron. So since we are having 6 CN ligands, these 6 ligands will be providing 2 electrons each. Okay, so in order to accommodate those 2 electrons, this Fe3+ or the central metal ion should be ready with 6 vacant orbitals. See here, how many vacant orbitals are here now? 1, 2, 3, 4, 5, 6. So it should be ready with 6 vacant orbitals in order to accommodate the electrons donated by the ligand. And also those vacant orbitals should be hybridized in such a way that those orbitals should have equal energy. Okay, it should have equal energy as that of the orbitals of the ligands. Okay, so this CN will also be having orbitals, and this orbital should be equal in energy with the orbitals of the central metal ion. So in such a way, these orbitals will be getting hybridized. So based on this principle, this Fe3+, what it will do, can now provide 2 3d orbitals, 1 4s orbital and 3 4p orbitals for complex formation with 6 CN ligands, which can provide 2 electrons each, and thus it undergoes D2, is it not, D2sp3 D2sp3 hybridization. It undergoes D2sp3 hybridization and it forms inner orbital complexes. Okay, see what are the orbitals undergoing hybridization? The 2 orbitals of this D and then 1 S and 3 p orbitals will be undergoing hybridization, and it forms D2sp3 hybridization. And after undergoing this type of hybridization, all these orbitals will be having equal energy as that of the ligand, orbitals of this ligand. Okay, so this is how these vacant orbitals will be. Okay, D2sp3 hybrid orbitals, these are vacant. 1 2 3 4 5 6 orbitals are vacant now. So this is the hybridization. Okay, now how the orbitals will be filled? Okay, see here, 1 2, so 5. Okay, and now it is unpaired. Now how will be the D2sp3 hybrid orbitals in the complex? See, after the formation of the complex, how these orbitals will be? See, let me write. This will be as such. Here will be having 2 electrons, here also will be having 2 electrons, this will be having 1. So what happens is this, the D2sp3 hybrid orbitals of the central metal ion will be overlapping with the orbitals of the ligands. Okay, it will be overlapping with the orbitals of the ligands, and it finally forms the this cyanide will be, these cyanide ligands will be giving electrons, and those electrons will be getting accommodated in this vacant hybrid orbitals of central metal ion. Okay, so how, see this is the lone pair of electron provided by first cyanide, and this one is the second, and this one is third, fourth, fifth and sixth. Okay, so this is how the electrons will be getting accommodated. So 6 pairs of electrons. Okay, 6 pairs 6 pairs of electrons from 6 cyanide Cn minus ligands, okay, and those electrons will be getting accommodated in the hybrid orbitals provided by the central metal ion, that is Fe3 plus. Understood? So now look at the geometry. See, geometry, it is octahedral complex, so it is having 6 cyanide. See, this is the structure, so it is octahedral complex, okay, octahedral, okay. Next comes the magnetic property. See, after forming the complex, we should check the orbitals whether it is having any unpaired electrons. See here, see, after forming the complex, let us check here. We are having one unpaired electron. Since it is having one unpaired electron, it is paramagnetic in nature. If all the electrons are paired up, then it will be diamagnetic. Since it is having one unpaired electron, it is paramagnetic. Understood, students? Okay. Now we can calculate the magnetic moment. How to calculate magnetic moment? See, there is a formula. Mu S is equal to root of n into n plus 2, where n is the number of unpaired electrons. See here, we are having one unpaired electron, is it not? So n is equal to 1. If n is equal to 1, we can substitute the value here, 1 into 1 plus 2. Okay, so it is root 3. What is root 3? It is 1.73. What is the unit for magnetic moment? It is Bohr magneton. It is Bohr magneton. Understood? So this is how we should calculate the magnetic moment for a complex. Okay. Fine, students, you might have understood clearly how VBT is used to explain the hybridization, geometry and magnetic properties of FeCN6 3n-. We'll meet you with another set of example in my next video. Until then, it's Dr. Anita Raj signing off from you. Thanks for watching.